So how do we actually measure the change in internal energy for chemical reactions? Well, we have to look at the system and its surroundings. So a system exchanges energy with the surroundings through two methods, heat and work. And we've looked at both of these now. Heat can be quantified as the mass times the specific heat capacity times the change in temperature. And the work is negative P external times the change in volume. These could both have the same sign, whether positive or negative. One could be positive and one could be negative. The net flow of heat could be from surroundings to system or from system to surroundings. Just depends on the magnitudes of those numbers and their signs. So when we look at the change in internal energy during a chemical reaction, we're looking at measuring all the energy, both heat and work, that's exchanged with the surroundings. So we can say that the change in internal energy is equal to the heat plus the work for that system. Well, what if there's no change in volume? Because maybe we don't allow a change in volume. It's in a container with rigid walls. The volume cannot change. Well, we're talking about pressure volume work, right? So work is equal to negative P delta V. Well, if the change in volume is 0, it doesn't matter what the pressure is, the work is 0. And so that makes this term go away, which makes the calculation much simpler. And so we can say that delta E for the reaction is equal to Q. We put a subscript V here to indicate that this is happening at constant volume. Okay. So it's not practical to observe the temperature changes of individual chemicals. Just like putting that block of metal in the water, we can't observe the temperature change of that piece of metal unless we had a thermometer like embedded in it beforehand. And how often does that happen? Never. So what we do is we measure the temperature in the surroundings, and then we know that the energy or the heat gained by the surroundings is what was lost by the system. So the number's the same, we just change the sign. We use surroundings where we can measure things nicely. And we need the surroundings to be controlled, and we need them to be insulated, because we don't want the surroundings to be the universe, because that's a little hard to measure. We want the surroundings are whatever is around the system that it exchanges energy with. And so if we design that carefully, we can say, well, there might be a tiny bit of loss of energy, but essentially it's all going to stay here. So one thing we can use is called a bomb calorimeter. So Q for the system is equal to negative Q for the surroundings. Right, so the system loses heat, the surroundings gain. The system gains heat, the surroundings lose. Same number, just change the sign. So now we're going to make the surroundings a calorimeter. It's really a thing for measuring calories, for measuring heat. So calorimetry is a technique used to measure the heat of a reaction by observing the change in temperature of the surroundings. So we have our system. It's exchanging heat with the surroundings. We observe the temperature change. We can measure the mass and the specific heat capacity of the surroundings. And so we can calculate the heat that was exchanged. We set this up so that the change in volume is 0, and then we don't have to worry about the work term. So this is an illustration of a bomb calorimeter. This is the bomb part in the middle. So inside here is a tightly sealed container, and you put your sample in here. These are used to measure energy changes for combustion reactions. So you might wonder, well, how do they know that this piece of candy has so many calories in it? One way to do that is to actually burn it and measure how many calories of heat energy are given off. It's easier to think of something like a peanut or, some grass or something combustible, but you can make candy burn too. It's sugar. So you put your sample in here, and this bomb has a lot of oxygen in it because oxygen is necessary for combustion. And then we have ignition wires here so that we can use an external trigger to give a spark in here and start the combustion. Because we can't just sit around and wait for it to spontaneously combust. That's really, really boring. The calorimeter then is on the outside, and it's going to be, so this is tightly sealed so that the volume can't change. So even if this were to explode, the volume's not going to change. Outside we have a container filled with water. So the heat that's lost by this combustion reaction is going to get transferred into the water surrounding it. And this container is going to be well insulated, like a really good, maybe like a Yeti, right? So you put hot coffee in the Yeti and you seal it up and you wait maybe 10 minutes and you feel the outside of the Yeti. Is it warm? No, because there's a vacuum in there that doesn't allow the heat to transfer, and that's how it keeps your coffee hot or your cold drink cold, right? It's well insulated. So think of this as a Yeti for science. So the water heats up, and we've got a thermometer in here. We can measure the initial temperature of the water. We can measure the final temperature of the water. We've got some sort of stirring mechanism in here because the heat is going to be generated here, and it's going to slowly move out, and we want to be able to measure it accurately. We want the heat to be distributed into all of the water. So we have a little stirring mechanism here. So, assuming that no heat escapes, which means that it's a well-designed calorimeter, Qcal is equal to the heat capacity for the calorimeter times the change in temperature. Now here we're actually using heat capacity rather than specific heat capacity. We measure the heat capacity in a separate experiment where we know how much energy is going to be released, and we measure the temperature change of the calorimeter. The heat capacity is useful here instead of specific heat capacity because the mass of the calorimeter is not changing. We're going to put the same amount of water in it every time. It's always going to be the same. Heat capacity is specific heat capacity times mass. So we just lump them together for the calorimeter. So we're going to measure the change in temperature for the calorimeter, multiply it by this constant, and that's going to be equal to the heat given off by the reaction. So the change in energy for the reaction is equal to Q for the reaction. So Qcal is equal to negative change in internal energy for the reaction. It's a lot. Any questions? This is an example of one of the things I think is really cool about science is there are things that you cannot observe directly. And so in science, what we do is we figure out, how can we observe the effect of this thing so that we can figure out what it is even though we can't actually measure it? And so here we can't measure what's going on in here, but we can measure how it affects the surroundings and then figure out what went on in there. So here's a bomb calorimeter problem. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 to 38.13 degrees Celsius. This is a fancy piece of equipment, and so we use a better thermometer in here. It's not just one of those glass ones. It's going to have better precision. We're asked to find the heat of, or the change in energy for the reaction in kilojoules per mole of hexane. And we're told that the heat capacity of the bomb calorimeter is 5.73 kilojoules per degree Celsius. So let's harvest numbers and see what we get, what we can do with them. Okay, so we've got 1.550 grams of liquid hexane. That might be important. That's C6H14. Temperature rises from, so initial temperature is 25.87. Final temperature is 38.13. Do you think we're going to need the change in temperature? Probably. Let's just calculate it right now. Whoops. So the change in temperature is the final 38.13 minus the initial 25.87, 12.26 degrees Celsius. And then we're told that the heat capacity of the calorimeter, so that's C for the calorimeter, is 5.73 kilojoules per degree Celsius. So we want to find delta E for this reaction. In the bomb calorimeter, the volume cannot change, and so the change in internal energy for the reaction is equal to Q for the reaction, which is equal to negative Q for the calorimeter. Because the reaction is losing its heat to the calorimeter. The calorimeter is gaining the heat. The amount of heat is the same. It's just positive or negative depending on your point of view, right? Like transferring money. So we want to find this delta E, our Xn. So that's going to be equal to negative Q cal. So let's start that up here. Delta E for the reaction is equal to negative Q for the calorimeter. Well, we're accustomed, or should be accustomed, to Q equals MC sub S, delta T. The specific heat capacity. This part right here together is heat capacity. And that's what we're given here. Notice there's no gram term in the bottom. So Q calorimeter is negative C calorimeter delta T. We don't need the mass in this calculation here, and what we would need for mass is the mass of the calorimeter, and that's the mass of the hexane that burns. So that mass wouldn't work anyway. So we put this in here, and this is where units can be really helpful. So 5.73 kilojoules per degree Celsius, and that's multiplied by 12.26 degrees Celsius. The degrees cancel out and we have kilojoules. We don't need the mass because the mass is included in the heat capacity of the calorimeter. Yeah.
So it's probably not specific.
With the bomb calorimeter, they're not going to give you mass and specific heat. They'll give you just the calorimeter constant. Yeah. And we'll see that these are really cool, but they're also really expensive. And so we're not going to do experiments with them. So these are just going to be book problems with bomb calorimeters. So if we do the math here, negative 5.73 times, well, that's wrong, 0.73 times 12.26, negative 70.2498 kilojoules.
Does the negative only apply to the C pi or apply to the C cal delta T?
The negative applies to the whole thing. Yeah. We're just we're calculating Q cal and we're changing the sign. So it's like multiply it by -1. It's a really, really simple concept, and yet it is often really confusing. I think because it's so simple, our brains are just like, wait, what? If I give you $10 what's the change in your financial status?
19.
Yeah, so you get plus 10. What's the change in mine? Negative 10, right? And whether it's positive or negative just depends on what side of the transaction we're looking at, right? So here, if we're looking at the bomb calorimeter is gaining energy, but the reaction lost energy. And so we're calculating the change in energy for the reaction, so we need to adjust the sign accordingly. Reaction lost, calorimeter gained. Losing is negative. So this would have 3 significant figures. So I calculated a delta E in units of kilojoules. Does this answer the question? No. This is the amount of energy in kilojoules that is released when 1.550 grams of hexane burns. Well, whoever needs this change in energy, are they always going to burn 1.550 grams of benzene? No. They'll probably never do it again. It'll be some different amount. So we want delta E to be kilojoules per a certain amount of stuff that burned. So it was this many kilojoules for this many grams. But I want it in moles for whatever reason. Can I figure out how many moles this is? 1.550 grams of C6H14. I just need to calculate the molar mass.
Can I interrupt you real quick?
Mm-hmm.
So you mentioned that the reaction is negative, but in this equation right here underneath where it says delta E reaction, you have reaction as positive.
Okay, so this is something that's hard to get our minds around. This variable is positive, but the value of it could be positive or negative. And the negative sign here is just saying that this is opposite in sign to the other one.
Okay.
So if Q reaction is negative 5 joules, then Q cal is positive 5 joules. Yeah. Because I can take this equation and I can divide both sides by -1 or multiply by -1 and just, oops, I'm dragging something else here. But then I've got this other thing over here too. Right? So you can multiply both sides by -1 and move the negative sign to the other side of the equality.
So the negative sign is subject to depending on which one's gaining, which one's losing.
Yeah, when you look at the numbers associated with the variables, which one is negative and which one is positive will depend on which way the heat went. Yeah. Okay, so 6 times 12.01 plus 14 times 1.008 molar mass of hexane. I think I said benzene earlier. Just disregard that. It's whatever the problem says. So 1.550 divided by the molar mass. I did something wrong. A syntax error. Yeah, crazy thing, it wants me to use the divide button. I figured. 0.179872 moles. So the change in energy for the reaction was negative 70.2 kilojoules when 0.01798 moles reacted. How do I get kilojoules per 1 mole? I divide. And so this part is not an equation that you can look up. You have to think about it and put it together. So delta E for this reaction in kilojoules per mole is negative 70.2498 kilojoules for every 0.0179872 moles. Three sig figs. How should I record that? Minus 391? Yeah. I've lost a decimal place. I need to replace that 5 with a 0. Because this is negative 3,905, which is not even close to minus 391, right? So we have to keep the magnitude the same. So when I'm rounding past the first place, the ones place, I need to be careful to replace everything up to the decimal point with a 0. So minus 3910 kilojoules per mole. Or, I'll squeeze it in up here, minus 3.91 times 10 to the third kilojoules per mole. If I put this number in scientific notation, I'm saying, okay, the 3.9, and I'm going to stop here, so that rounds up to 1. And then times 10 to the, and I look, how many places do I move the 0, I mean the decimal? 1, 2, 3, 10 to the third. I don't have to worry about filling in with placeholder zeros. So if you have a tendency to make rounding mistakes here, put it in scientific notation and then round it. Any questions? Minus 3.91 times 10 to the third kilojoules per mole. Now that seems like a big number, right? But joule is actually a very small energy unit, and these types of reactions do generate significant amounts of heat. So here we're going to sometimes see very, very big numbers. And you just have to be okay with it.